Our world is a symphony of movement. Rivers flow, winds whisper across vast plains, and life, in all its magnificent forms, is in constant motion. For humanity, this movement has increasingly been powered by machines. For over a century, the internal combustion engine has been the dominant force, a powerful but hungry beast that has fundamentally reshaped our landscapes and our atmosphere. Now we stand at a remarkable turning point in our history. We are witnessing the dawn of a new era, not by fire and fossilized sunlight, but by the silent, steady flow of electrons. This is the age of the electric vehicle, a technology that holds the promise of a cleaner, quieter world. The heart of this revolution, the very pulse that gives it life, is the battery. This remarkable device is the reservoir of energy, the silent powerhouse that enables these vehicles to glide through our cities and across our continents. The quality, capacity, and sustainability of this battery technology will ultimately determine the success of this grand experiment. Consider the humble battery not merely as a component, but as the linchpin of a new industrial ecosystem. The challenges are immense, of course. We must find ways to store more energy, to recharge it more quickly, and to do so using materials that are abundant, affordable, and sourced with minimal impact on the natural world. And so, our story begins here, with this quest for a better battery. We will look beyond the technologies that have brought us this far and gaze toward the horizon, where new and extraordinary solutions are beginning to take shape. It is a story of hope for a cleaner, more sustainable future for all life on Earth. For now, one element reigns supreme in the world of electric energy storage: lithium. This light reactive metal has become the cornerstone of the modern battery. Its ability to store a great deal of energy in a small, lightweight package has made it the undisputed king. Lithium-ion batteries power our phones, our laptops, and most significantly, the vast and growing fleet of electric vehicles traversing our roads. The rise of lithium has been swift, and its dominion for the moment seems absolute. But like any monarch, the reign of lithium is not without its challenges and its costs. This remarkable element is not infinitely abundant. It is concentrated in only a few places on Earth, often in fragile ecosystems. The process of extracting it can be incredibly demanding on the local environment, requiring vast amounts of water in some of the driest places on our planet. This creates a profound dilemma. In our very effort to build a cleaner technology to save our environment, we risk causing significant harm to the specific habitats from which we draw our raw materials. Furthermore, the world's reliance on a handful of geographical locations for its lithium supply creates a delicate and often volatile geopolitical landscape. The supply chain is long and fraught with potential disruptions, from political instability to economic competition. This fragility is a source of great concern for an industry that is growing at an exponential rate. As millions more electric vehicles are built each year, the demand for lithium is set to soar, placing ever greater pressure on these limited resources and the communities and ecosystems that surround them. And then there is the matter of safety and longevity. While generally reliable, lithium-ion batteries contain a flammable liquid electrolyte. The very success of the lithium-ion battery has, in its own way, exposed its limitations and sent scientists and engineers on a new and urgent quest for what comes next. Just as nature abhors a vacuum, the world of science and engineering abhors a limitation. The challenges posed by lithium have not led to despair, but rather to a furious burst of creativity and innovation. All around the globe, in laboratories and research institutions, a new generation of battery technologies is being born. These are the challengers, the pretenders to lithium's throne. They are being developed from different elements, using different principles, and they hold the potential to once again revolutionize our relationship with energy. It is a thrilling race, a quiet but momentous competition to discover the next great power source. Among these rising stars, a few shine particularly brightly. We hear whispers of sodium-ion batteries. They seek to replace rare lithium with a far more common element, sodium. Then there are solid-state batteries. They replace the liquid electrolyte with a solid, promising safety and higher energy density. And we see the astonishing potential of graphene, a material so thin and strong it could enable charging in seconds. Each alternative represents a different path forward. They are not mere variations on a theme. They are fundamentally different approaches to storing and releasing electrical energy. Some focus on reducing cost and increasing sustainability with earth-abundant materials. Others focus on dramatically improving performance, pushing range and charging speed to make EVs unquestionable. Different applications require different batteries. A small city car, inexpensive, robust sodium-ion. The dawn of this new era is upon us. Imagine the vastness of our planet's oceans, a repository of life and immense chemical wealth. Within every drop of seawater is an element we all know. Sodium. Sodium. It is the Na in nasal, table salt, one of the most abundant elements in Earth's crust, now at the center of exciting battery developments. The sodium-ion battery works like its lithium cousin. It shuttles sodium ions between a positive electrode and a negative electrode during charging and discharging, creating a flow of electricity. The primary advantage is abundance. Sodium is over 1,000 times more common than lithium. It can be sourced from seawater or from vast salt deposits found all over the world. This geographical diversity changes the resource equation. It frees the supply chain from dependence on a few locations, democratizing access to energy storage materials. This could dramatically lower battery costs, making electric vehicles more affordable for millions who are currently priced out of the market, and reducing geopolitical tensions associated with resource scarcity. However, nature rarely offers a perfect solution without a trade-off. The sodium ion is physically larger and heavier than the nimble lithium ion. This means that, for now, sodium-ion batteries cannot store as much energy in the same amount of space as lithium-ion batteries can. Despite these hurdles, the progress has been astonishingly rapid. The Chinese company CATL recently unveiled its first-generation sodium-ion battery. These batteries are proving to be exceptionally robust in cold weather. While they may not be ready to power a luxury long-range sedan just yet, they are a perfect fit for smaller city cars, energy storage for the power grid, and two-wheeled electric vehicles. For decades, the basic architecture of a battery has remained the same. Two solid electrodes separated by a porous membrane and soaked in a liquid electrolyte. It is this liquid that allows ions to travel back and forth, but it is also the source of many of the battery's limitations, including its flammability and gradual degradation. Now, scientists are on the verge of a monumental change, a shift in the very state of matter within the battery. They're aiming to replace this volatile liquid with a solid material, a thin, stable layer of ceramic or polymer. This is the simple but revolutionary concept behind the solid-state battery. The promise of this technology is immense. By eliminating the liquid electrolyte, solid-state batteries can be made far safer. The risk of fire could be virtually eliminated. This solid separator acts as an impenetrable barrier, preventing the growth of tiny metallic filaments called dendrites. Dendrites can cause short circuits and kill a lithium-ion battery. Safety and stability open the door to more energy-rich electrodes, such as pure lithium metal, too reactive for liquid electrolytes. The benefits for an EV driver would be extraordinary, potentially twice the energy density in the same volume, a driving range of 1,000 kilometers or more on a single charge, eliminating range anxiety, dramatically faster charging, 80% in the time it takes to drink a cup of coffee, 10 or 15 minutes. Refueling an EV nearly identical to petrol. Challenges remain. Manufacturing thin, flawless, solid electrolyte layers at scale is incredibly difficult. Keeping perfect contact as materials expand and contract is a huge engineering puzzle. Companies are investing billions. Toyota, Volkswagen, QuantumScape. Breakthroughs are happening now, but mass-market solid-state batteries may still be a few years away. Their arrival will mark a new epoch for electric mobility. In the world of materials science, there are moments of discovery that really redefine what we believe is possible. The isolation of graphene in 2004 was one such moment. Graphene is a truly remarkable substance. It is a single layer of carbon atoms, arranged in a perfect hexagonal lattice, like a sheet of atomic chicken wire. It is the thinnest material ever created, yet about 200 times stronger than steel. It is almost completely transparent, and an exceptional conductor of electricity and of heat. These properties have made graphene a candidate to revolutionize countless fields, battery technology being one of the most promising. Graphene isn't used to make a battery by itself. Instead, it's added as a powerful additive, a secret ingredient, that enhances existing battery chemistries. Lithium-ion, sodium-ion, its electrical conductivity improves electron flow inside electrodes. Think of it as building superhighways for electricity in the battery, so it can charge and discharge much faster. Its immense surface area gives more places for ions to attach, which can increase overall energy storage capacity. The biggest impact could be charging speed. Current batteries are limited because forcing too much energy in too quickly can make them overheat and degrade. Graphene conducts electricity efficiently and conducts heat efficiently, helping manage heat and energy flow. A graphene-enhanced battery could recharge in a fraction of the time of a conventional one, charging an electric car in minutes, not hours. That would remove a major barrier to mass EV adoption. The promise is clear, but widespread use is challenging. Producing high-quality, defect-free graphene at scale is difficult and costly. For example, GAC Aeon launched a vehicle in China with a graphene-assisted battery, claiming 0-80% in 8 minutes under specific fast-charging conditions. When we place the old king, lithium-ion, alongside these new challengers, we see a fascinating story of trade-offs and evolution. It is not a simple case of good versus bad, but a complex tapestry of strengths and weaknesses. In terms of performance, lithium-ion is the well-understood benchmark. It offers a balance of energy density and a respectable lifespan. Solid-state batteries promise to shatter this benchmark, potentially doubling energy density, leading to vehicles with vastly superior range. On the other side is the sodium-ion battery. Today it can't match lithium in pure energy density. A same-weight sodium pack will have a shorter range, for now, but it shines in other crucial areas. Its potential for lower cost may be its greatest strength. Environmentally, the comparison gets more compelling. The mining of lithium and cobalt carries heavy environmental and social costs. Mining is water-intensive and concentrated in a few regions, raising ethical concerns about labor practices and ecological damage. Sodium-ion batteries have an advantage here. Raw materials are abundant and easier to extract. Solid-state batteries, even if they use lithium, could cut the need for problematic materials like cobalt and graphite, and their longer lifespan means fewer batteries produced and recycled. Finally, safety and longevity matter. Lithium-ion has a proven track record but contains a flammable liquid, a small but persistent safety concern. Sodium-ion is inherently safer and can be fully discharged for transport. Solid state represents the ultimate prize with a non-flammable solid electrolyte. Chemistries age differently. Lithium-ion has a known degradation curve, while new sodium-ion and solid-state designs are built for enhanced cycle life, promising batteries that could last millions of kilometers. Each technology brings unique advantages and challenges, creating a diverse ecosystem where different solutions serve different needs. The future belongs not to a single winner, but to a portfolio of complementary technologies. We live on a planet of cycles. Water evaporates from the ocean, forms clouds, returns as rain. Seasons turn and life adapts and endures. For a long time, our technological progress has felt linear and extractive, a one-way street of taking from the earth. But what we are witnessing now in the world of battery technology feels different. It feels more like a natural cycle, a process of learning, adapting, and evolving toward a more sustainable and harmonious state. The future of electric vehicles may not, in fact, need to be singularly reliant on lithium. Instead, it appears to be a future of rich diversity. We will see affordable city cars powered by the salt of our oceans, their sodium-ion hearts beating reliably and affordably. We will see magnificent long-range vehicles powered by safe and energy-dense solid-state cells, capable of crossing continents in silence and without emissions. And woven into these technologies, we may find the miraculous properties of graphene, enabling charging speeds that we once thought were the stuff of science fiction. Each technology will find its niche, its own place in the ecosystem. This journey is about more than just building better cars. It is about fundamentally rewiring our energy system. These new batteries will do for renewable energy what the reservoir did for the aqueduct, allowing us to capture and store the intermittent power of the sun and the wind, and use it whenever and wherever we need it. They are the key to unlocking a truly clean and stable global power grid. This frees us from the geopolitical and environmental burdens of fossil fuels, offering a path toward greater energy independence and a more stable climate. As we stand here on the cusp of this new era, it is impossible not to feel a sense of profound optimism. The challenges are still great, and there is much work to be done. But the direction of travel is clear. The human mind, when faced with a great challenge, is a force of incredible creativity. We are learning to work with the elements of our world in smarter, cleaner, and more sustainable ways. The silent electric revolution is gaining momentum, and with these remarkable new batteries on the horizon, its potential seems truly boundless. A cleaner, quieter, and more vibrant world is not just a possibility, it is being charged into existence.